Hi, welcome to my channel. I am Aravindan. This is the third lesson in electric field. During the first lesson, I discussed the theory part about electric field strength, Coulomb's law. Then the second lesson, I discussed some questions. In this lesson also, I'm continuing discussing some questions and I'll do some other theory part also, right? Okay, so I gave the URL of the first two lessons in the description of this video, so you can watch that also if you want. Okay, so this is the fifth question we are going to discuss in this lesson. Okay, so there are 2-point charges, 20 nanocoulomb, 20 nanocoulomb, both are positively charged particles, are kept at 2 points, right? And the question is very simple. They ask you to find the electric field strength at point P. So the point P is at the same distance from both charges, 5 centimeter, and this line, the horizontal line, is making an angle of 40 degrees with both these lines. Okay, so how to find the answer for this? Okay, so answer I can say like this. So if I want to find the direction of electric field strength, I told that earlier, we should imagine if we keep a positive test charge at that point, what will be the direction of electrostatic force acting on it will be the direction of the electric field strength at that point, right? If I keep a positive test charge at P, this is also a positive charge, so it will repel. So I can see the electric field strength of 20 nanocoulomb. This charge, I can name this X, Y. So due to the charge at point X, the electric field strength at point P will be along this line. I can name it E1. Same way, the electric field strength due to the point charge at point Y at point P will be along this line. So that will be along this line. I can name it E2. So this will be, these angles will be 40 degree. And this also 40 degree. Okay, so I'll draw it here again, the point P. So at point P, this is the point P. So this is the point P. So E2 will be this direction. E1 will be along this direction. And this is 40 degree with horizontal. This is also 40 degree with horizontal, right? So both will have the same magnitude because these two charges are same magnitude and they are at the same distance, 5 centimeter from P. So if I find the electric field strength of one of it, either E1 or E2, that is enough to find the total, the final resultant electric field strength at point P. And we know the equation for electric field strength. It's given by E equal KQ over R squared. Yeah, E equal KQ over R square. I'm going to use that. So I'll find it for E1. That will be E1 equal K is 9 into 10 to the power 9. Actually, 8.99 10 to the power 9. But I have used 9 into 10 to the power 9. It's easy, right? Q is 20 nanocoulomb. So 20 into nano means 10 to the power minus 9 over R square. R square is 0.05 squared. Okay, that is the E1, right? I don't need to solve it because if I resolve these two in vertical direction, both will have the same magnitude. So E2 also will be the same because same charge, right? Same charge, 20 nanocoulomb like this, same distance. So that also will be the same. So the resultant electric field strength, you know, you would have actually, that's the end of electric field. I'm going to use the resolving vector concept of finding the resultant vector, right? So to find the resultant vector, I should resolve both these vectors into horizontal direction and vertical direction. So when I resolve them into vertical direction, E2 cos 40 will be upward, sorry, E2 sin 40 will be upward direction. This E1 sin 40 will be downward direction. Both have same magnitude, so the vertical components will get cancelled. So the horizontal component of these two vectors will be towards right. So the resultant force at point P will be, that I can call ER, will be towards right. The vertical components are going to get cancelled. So the horizontal resultant vector, resultant electric field strength will be towards right. That will be E1 cos 40 plus E2 cos 40. But E1 and E2 have the same magnitude. You can find it and you substitute here. You will get the final answer. That will be 11 into 10 to the power 4 Newton per Coulomb. Substitute this value, solve it, substitute here. Both have the same magnitude. Find the cos 40. This final answer. The resultant vector will be 11 into 10 to the power 4 Newton per Coulomb towards right. Yeah, already I mentioned the direction here. Okay, second part, they ask me to find the resultant force, the electrostatic force acting on a point charge minus -2 nanocoulomb when it is kept at point P. So I know the resultant electric field strength at point P, I already found it. So the resultant electrostatic force acting on -2 nanocoulomb, I can find by using F equal QE. Q is the 2 nanocoulomb. So 2 into 10 to the power minus 9 into the electric field strength, already we found it, 11 into 10 to the power 4. So the answer will be 2.20 into 10 to the power minus 4 Newton. So what will be the direction? Say, I told yesterday also, if you keep a positive charge particle in electric field, it will experience electrostatic force along the direction of the electric field. Okay, whenever you keep a positive positive particle in electric field, it will experience electrostatic force along the direction of field lines. If you keep a negative charged particle in electric field, it will experience electrostatic force opposite the direction of field line. So I already showed the direction of the field line at point P is towards right. So the electrostatic force acting on -2 nanocoulomb, we found it, the magnitude, the direction will be opposite to the direction of electric field. That will be towards left. Okay, now we are going to learn about, so far we learned about point charges, how to find the electrostatic force between 2 point charges, how to find the electric field strength created by a point charge at a distance r from it. Okay, now we are going to learn about how to find the electric field strength created by a sphere, metal sphere, conductor sphere, which has uniform distribution of charge on its surface, right? Actually, we don't go deep in this topic. Actually, we need Gauss law. Gauss law is not in Edexcel, Cambridge, and in national baccalaureate syllabuses. So I'm not going to go in deep about the Gauss law, its application, mathematical parts. That will be discussed in separate video with advanced electrostatics, right, including the mathematical part, everything. So here just I'll tell you about how to handle this type of situation. Okay, now when you charge a metal sphere, solid metal sphere, not a hollow, a solid metal sphere, what happens? The charge will stay on its surface. It never stays inside the metal sphere. It always stays on the surface of the metal sphere, right? So if a metal sphere is charged, when it is charged, right, all the charge, say it's charged to positive, it carries positive charges, then the charges should be uniformly distributed on its surface, right? It will be, because it's a sphere, uniform surface. So the charges will be uniformly distributed on its surface, and let the radius of the sphere is capital R. If the radius of the sphere is capital R, right? Okay, so if the total charge on the surface is Q, right, according to your syllabus, we say that actually the real theory related to that is the Gauss law. The word Gauss law is not used in Edexcel, Cambridge, as well as IB syllabuses, but in your syllabus they say we can assume the whole charge is concentrated at the center, right? That is a Gauss law actually, right? So we can assume the whole charge distribution on the surface we can assume it is concentrated at the center of the sphere. But actually that is not the case. They are distributed on the surface, and it should be distributed uniformly, equally on its surface. But we assume the charge Q is concentrated at the center of the sphere, right? So if the charge Q is concentrated on the sphere, I can assume like this: the whole charge is at the center, right? Then you might try to find the electric field strength inside the metal sphere, somewhere here at a distance r, where r is less than r. You might try to find by using E equal kq over r squared. No, that is wrong. Actually, when a metal sphere is charged, since the charges are distributed on the surface, the electric field strength inside the surface will be equal to 0. Inside a metal conductor, or metal means it's a conductor, inside a conductor there won't be any electric field. Remember that. So inside the metal, the electric field strength will be equal to 0, right? So what will be the electric field strength on the surface? That we can find. On the surface, the electric field strength is given by assuming the whole charge is distributed on the center. I can say E equal kq over r squared. Okay, so that is the electric field strength on the surface of the charge, kq over r squared. Okay, inside the sphere, the electric field strength inside the sphere, the electric field strength at any point will be equal to 0. Then when you go away from the surface, the electric field strength will decrease according to inverse square law. Okay, the electric field strength will decrease according to inverse square law. So I can draw the graph of electric field strength against distance. I can draw like this. I can say this is the y-axis, electric field strength, and this is the distance from the center. I measure it from the center. So up to the radius, the electric field strength will be equal to 0. So I can draw up to the r, until d becomes equal to r. R is the radius, capital R. The electric field strength will be equal to 0. Then on the surface, the electric field strength will be E equal kq over r squared. So that will be a value. I can put that value, this one, that is kq over r squared. Then it will decrease according to inverse square law. So I can draw, but it never comes 0. Only at infinite distance it will become 0. It will decrease like this. Right? It will decrease like this. It won't come to 0. It will decrease like this. So I can draw a line here also, no problem. Okay. So in your syllabus, we consider only the conductor, right? If it is insulated, it can have charge inside. Then we need to consider volumetric charges. Yes, we can find there also, but not in your syllabus. So I don't want to do that in this video. I'll do it separately in an advanced electrostatics, something like that. I'll do it later. Okay, good. This is the question based on metal sphere. So in this question, metal sphere of radius 2 centimeter carries uniform distribution of 10 microcoulomb on its surface. So first part, they asked to find the electric field strength at a distance of 1.2 centimeter from the center O. Okay, you know 1.2 centimeter is inside the metal sphere. So the electric field strength inside the metal sphere will be equal to 0. So the first part answer is simple. I don't need to do any calculation. So first part, I can say E equal 0 inside the metal sphere. I already told that just now. Okay, second part, find the electric field strength on its surface. So I can assume, I already told that the whole charge is concentrated at its center. That's the way we take based on Gauss law. The word Gauss law is not in the syllabus. Okay, second part, I can say E equal kq over r squared. So K is 9 into 10 to the power 9. Q is 10 microcoulomb, 10 into 10 to the power minus 6 divided by R square, 2 centimeter, convert to meter, so 0.02 square. If you solve, you will get 2.25, 10 to the power 8 Newton per coulomb. Right. Third part, find the electric field strength at a distance of 12 centimeter from its surface. So from its surface 12 centimeters. So we assume the whole charge is concentrated at the center. So from the center, the point they consider is at a distance of 12 plus 2, that is 14 centimeters, right? So in equation we can use, but only thing, instead of R, for R we should substitute 14 centimeter, convert to meter, 0.14 meter. So the third part, E equal K is 9 into 10 to the power 9, same equation I am using. So Q is 10 microcoulomb, 10 into 10 to the power minus 6 divided by 14 centimeters from the center, so 0.14 squared. So the answer will be 4.59, or we can say 4.60, no problem, no big difference anyway. 4.59, 10 to the power 6 Newton per coulomb. Okay, so this is the question for another question based on metal spheres. So here there are two identical metal spheres. Mass of each metal sphere is 15 grams and they are carrying same magnitude of like charges. So they are connected by two separate strings, non-conducting strings. Each length is 29 centimeter. Length of each string is 29 centimeters, right? So the radius of each sphere is 1 centimeter. Radius of each sphere is 1 centimeter. So the distance of the center from O will be 30. This also 30. And they are saying the surfaces are, the two metal spheres are 6 centimeter apart from surface to surface. So from center to center, they will be 8 centimeter apart. Is it 1 centimeter? 6 plus 1 plus 1, 8 centimeter apart. Okay, so first part, draw a free body force diagram. So you know both spheres will experience same magnitude of electrostatic force and it will be a repulsive force. That's the reason the metal spheres are moved further apart and their weight will act at the center and the tension will be along the string. So first part, they ask to draw the free body force diagram for the sphere X. So that you can draw like this. This is the sphere. The weight will be from the center because it's a uniform sphere, right? So that is the weight. I can say mg. The tension will be along the string, so that I can say this way. This is the tension. And the electrostatic force will be horizontal because they are on the same line, same length, so it will be along the horizontal line. So the electrostatic force will be horizontally towards left. It won't be at any other direction because they are same length, so they are along the same line, horizontal line. So this is the answer for the first part. Okay, second part, they ask me to find the tension on the string. So both strings will have the same tension, so we can find the tension on one of the strings. Okay, so that we can find by using just resolving the forces and the condition for equilibrium. So T cos theta. So this angle, we don't know, we are going to find it. T cos theta, if you resolve it vertically, second part, T cos theta minus mg must be equal to 0 because it's at rest. It's at equilibrium, rest. But I don't know the theta. So this is the theta. This angle theta is this angle. I can use I can find by using sine theta, because this length is 6, the total length is 6, so this will be 3, this is 1, 3 plus 1, 4, this will be 30. So if I consider this triangle like this, and this is horizontally, that will be 4 centimeter, this will be 30 centimeter, because 29 plus 1, 30 centimeter, and I need to find this angle, so I can use sine theta equal 4 over 30, so theta will be, take inverse of it, you will get theta will be 7.7 degree. Okay, now use this equation. So if I consider vertically, t cos 7.7, is it? T cos 7.7 minus, the mass is 15 grams, it's given here, 15 grams. So 15 into 10 to the power minus 3 to convert to kilogram into 9.81 equal to 0. You know how to solve it. Take it to the right and divide by cos 7.7. You will get the tension that will be equal to 0.15 Newton. Okay, so third part, they ask me to find the electrostatic force X on X, right? So far I didn't use any concept related to electric field. Still I'm using condition for equilibrium, is it? So third part also I can use the condition for equilibrium. If I resolve the forces acting on weight, we know that weight is equal to 15 into 10 to the power minus 3 into 9.81. We already used it. Right, so if I resolve horizontally, because it's at equilibrium, t sine 7.7 minus electrostatic force Fe must be equal to 0. But I found the tension already in my second part. So electrostatic force Fe equal to t sine 70, that is t 0.15. We already found it. So that will be 0.15 times sine 7.7. So we will get that value, the electrostatic force will be equal to 0.020 Newton. Find it, check it, 0.020 Newton. Okay, the fourth part, they ask me to find the charge on each sphere. They say that the question, they said they carry, both spheres are carrying same magnitude of like charges. So if I take charge on one of the sphere is Q, then other one also will have the same magnitude Q. So they are carrying the same magnitude of charge. I can assume, since they are metal conductors, they will stay on the surface. We assume the charge is uniformly distributed on its surface. Even if they don't say in the question, we should assume like that, otherwise we can't handle it. Okay, so if the charges are uniformly distributed on its surface, then I can imagine the charge will be concentrated at the center, the same way the charge Q is concentrated at the center. I can use the Coulomb's law, F equal K Q1 Q2 R squared. The distance between the two charges is not 6. It should be from center to center, because we are taking the charges are concentrated at their centers. So I can use the Coulomb's law. I already found the electrostatic force in my third part, the previous part. Now I'm going to use F equal K Q1 times Q2 over R squared. That's the electrostatic force. Fe, I can say Fe, the electrostatic force. So the electrostatic force, I already found it, that is 0.02 Newton, 0.02 Newton. K is 9 into 10 to the power 9. Q same, Q times Q, I can say Q squared, right? Divided by R. Careful, most of the students make mistake, they put 6, no, 8, because center to center, because we assume the charges are concentrated at the center, right? So in this center to center, that is 8 centimeter, because each sphere has a radius of 1 centimeter, it's mentioned here. So 1 plus 6 plus 1, 8 centimeter, convert to meter, so it will be 0.08 squared. Okay, 0.08 squared. So Q into Q squared. So if you want, I can write that step again. 9 into 10 to the power 9 times q squared divided by 0.08 squared. Solve it, find the q, you will get q 1.19 into 10 to the power minus 7 Coulomb, or I can say this as 119 nanocoulomb. So each sphere is carrying a charge of 119 nanocoulomb, but they might be positive, both, or negative because they are carrying like charges, same magnitude. Okay, so now I can ask an explaining type question. Okay, if I add more charge to only one of the spheres, say for example, only for sphere X, if I add more charge, now both are carrying 119 nanocoulomb. If I make the charge of X something like 150 nanocoulomb, by keeping the charge of Y the same, 119 nanocoulomb, what will happen to the position of the spheres? Okay, so that's a common mistakes. What students they say, this carries more charge, so this will move apart, this will remain the same. No, what will happen actually? What's going to happen? Now, when I increase the charge of one of the spheres, right? Say example, if I increase the charge of X, both are going to experience larger force. We calculated earlier that force was 0.02 Newton. It's going to be more than that, but both will experience the same magnitude of force, right? And since they have same weight, careful, since they have same weight, they will move apart such that the angle they make with the vertical line, again same angle but larger than what we calculated earlier. We calculated it as 7.7 degree. It will be more than 7.7 degree because the both spheres are going to shift through the same distance. Okay, they are going to shift through the same distance further apart, and the angle will become larger, but identical amount they will move apart. Okay, but if the weights are different, that will be different calculations. And how much distance will they move if they have different weight? Yes, we can calculate that also. That will be different approach. More calculations comes. I'll put those questions in my advanced electrostatic some other video, not in this one. Okay, right. So in this video also I calculated some questions. Next lesson, next video, I'll start about electric field lines and how to draw the electric field lines, and we'll go to uniform electric field, then radial field. Those things we'll discuss in the next video. Okay, right.